Hello.
Hello. Well, welcome to panel 1, Cognitive Architectures. We have two papers and their authors to talk about today. And so I'd like to start the panel by asking each of you to summarize your work. Just take a few minutes. I guess you could take up to 10 minutes summarizing your work. And then we will go by and ask questions individually, and then we will ask general questions. So welcome to the panel. We have Dr. Kolonin and Dr. Kovalev. Dr. Kolonin, could you please go first?
Hello again to everyone.
So welcome
Hello,
to
Eray,
the
also.
panel. We have
Hi there.
Dr. Kolonin and Dr. Kovalev. Dr. Kolonin, could you please go first?
I can hear some strong echo with some delay. I think it's from.
Deborah, if you can please turn off the sound on the stream, on the underline, or just close. Everybody who has underline site open, please close it. Otherwise, we can hear double sounds.
Yeah, I think for now it's cool. In my work in two words is about logical probabilistic biologically inspired cognitive architecture. So in my work, we present cognitive architecture based on some neurophysiological theory that is called theory of functional systems, that was developed in USSR and Russia by Professor Anokhin. And this architecture stands for its main point is goal-directed activity. So the main notion in this theory is that any activity is goal-directed, and we should think of any activity as about an activity to attain some goal, and each goal should be considered only with having a criterion of its attainment. Because if we don't have the criterion of goal attainment, we always can assume that the goal is already attained. So we have nothing to do. In my article, they discussed main points of this theory, such as afferent synthesis, acceptor of action results, motivational excitation, some afferentations like situational afferentation, triggering afferentation, and the main feature of our architecture of the biological theory and our architecture that was designed with respect to the biological meaning of the theory is that when the organism creates goal, and here I should mention that the definition of a goal is paradoxical by its nature, because we can have the goal, but but this does not imply that we have the instruction on how to obtain the goal. So this is called the goal paradox. And the brain function is to transform this paradoxical goal by this the theory says, the theory of functional systems, that the brain's main task is to transform this paradoxical goal into a non-paradoxical goal that provides information about how, by what means, and when we can obtain the goal. And this process is during this process concurrently the acceptor of action results, so-called, it forms the criterion or the hierarchy of criterions of the goal attainment. So the criterion of the final goal attainment and all its sub goals. and while the organism produces some actions to achieve the goal, they are measured and checked by the acceptor of action results if the actions are resultative for us. So this is the main concept of our architecture. Then we have the formalization, and the formalization is based on its rule-based cognitive architecture, and the rules are used by basic functional systems, and the complex functional systems consist of small functional systems, of basic functional systems, and each of basic functional system has a set of rules and their success probabilities, and the functional system's task is to choose the rules that are most probable to lead to success and use them, and check the result and measure it and change the weights of the rules, the probabilities of their success with respect to the result of the last action. And then we have some experiments that show how our architecture works in comparison with some other architectures based on Q-learning. That's it.
Okay, well, we have 2 more participants, so now we have a total of 4 papers to talk about. So I guess about 5 minutes each would be good. Dr. Kovalev, could you please continue?
Hi, everyone again. And in our work, we enriched cognitive architectural sound-based work model with hyperdimensional representations. Sound-based work model is an architecture that based on works of Vygotsky, Leontief, and Luria, like is psychologically based, and it has like main component of this architecture is a sign. This is a special structure with 4 components: image, meaning, significance, and name. And each of these components is presented as a special structure called causal matrix. And in our recent work, we considered the image component of a sign, and we changed the causal matrix with a high-dimensional presentation, hyperdimensional presentation, and apply it to the visual question answering task. And that's it, I think.
Great. Okay, Dr. Du?
Hi. So our work is actually about the DSO cognitive architecture. It's about the global workspace theory. So you can imagine you have different functions. They are computable functions, and what you want to do is based on different inputs. You want to string pipeline dynamically based on the inputs to a certain output. That's actually the whole idea of our paper. The thing about it is that we actually basically for every function's arguments, we actually break it down to their argument types, and we formalize this, or rather we actually structure this as a planning problem. So based on the input types of a function and the output type, we try to come up with a pipeline or a plan and a goal type. So we try to plan out a pipeline so as to achieve this certain goal type that we have. So the whole idea is you have different reasoners, all of them has different functions inside it. Through competition and attention, which we'll actually use to filter out based on the state of the system and the environment. We will try to plan out a pipeline for this. And yes, that's about it.
Okay, and Dr. Ozkural?
Dr. Ozkural, we can't hear you because you are muted. So if you can please unmute yourself and start again.
Hello there. Hello there. Sorry. Again. Hello there. My name is Eray. My paper is titled Omega, an Architecture for AI Unification. It is an introduction to our new AGI architecture, which is pretty ambitious. So it's really an overview, but it's a follow-up to Ray Solomonov's Alpha architecture, which is a modular, open-ended architecture that uses multiple problem solution methods using the universal induction approach. So this Alpha architecture of Solomonov can learn which problems work best for which problem solution methods work best for which problems, and then uses knowledge to allocate time to problem solution methods. But it also has a way to self-improve, so it can generate new problem solution methods. This is an open-ended architecture because it can evolve. As long as it solves problems, it can find better solution methods, and so can improve its performance. The Alpha architecture is based on Solomonov's work on general purpose or universal machine learning. So it in the basis, it uses something called a phase one machine. Phase one machine can solve general induction problems like set or sequence induction, and then it can also solve the update problem, which is transfer learning, a universal kind of transfer learning. So using this universal prediction and universal memory scheme, it can implement this modular architecture, which has multiple problem solution methods via the reference machine or universal computing model used by Alpha was a kind of a forth-like language. It's a simple recursive computer. Of course, we extend on this nowadays. So my work was using the scheme language for universal induction. So Omega extends Alpha considerably. We now have 8 reference machines. And this is based on an idea of Marvin Minsky. So, well, if you check out the paper slides, you'll see an architecture component diagram. And we have a general neural network model, which is called MetaNet, which can reproduce most deep learning architectures. And Church, which is a stochastic scheme variant, which is used as the glue language, sort of the scripting language of the system. And so it can use Church to do a bit of symbolic reasoning, symbolic computation, and use MetaNet to solve deep learning problems. But also it has many other languages like probabilistic logic, Bayesian network, an analog computer for robotics, picture for representing images, a matrix computer for representing scientific problems like a fusion reactor problem, and an asynchronous computer for event-driven or interactive computing. So using this very diverse set of representations, we extend the system's applicability. It becomes more general. And it's also seeded with many problem-solving methods from statistics and machine learning literature, because the goal is to automate data science. So we have a lot of built-in routines for clustering, classification, regression, outlier detection, and time series forecast, and deep learning, and an ensemble machine. We also extend the higher order cognitive modules in the Alpha architecture quite a bit. Alpha had an universal or ultimate ensemble machine, So we're going to be using deep learning methods to do that. And I added a dialogue engine using deep learning representations. The alpha architecture had analysis and synthesis, so it can decompose tasks or problems, analyze them, and solve subproblems and immersion, or synthesis, which can combine existing problem solution methods and generate new ones, which is a very powerful method. It can self-improve using the logic in Gödel machine. A self-improvement procedure runs continuously in the background. And we have intelligent agents. So I'm adding a new architecture called Zeus that has some autonomous exploration and imitation learning like capabilities for robotics. So this is basically what I've done, combining deep learning and symbolic kind of AI representations into the extremely powerful AGI architecture called Alpha. So we call it Omega, and I think a lot more material will be coming out. Thank you.
Okay. All right. Now let's proceed to the individual questions part of the panel. I would like to ask Dr. Kovalev. You propose an architecture with a reasoning engine that can either accept a binary attribute form that describes a scene or an embedding corresponding to the same form in which vector arithmetic can be used. So how does the inference with embeddings, for example, the distance-related ones, assist in the symbolic inference? For example, noting that all objects, telling which objects are to the right and that kind of thing.
Thank you for the question. First of all, I have to say that there are like two kinds of embeddings. First one is like word-to-vec or other embeddings that we can get from neural networks, and then they have this like semantic connectivity. So like this very famous example, if you take a word-vec for queen and extract man, then you will get a queen. But on the other side, there's vectors that you use in vector symbolic architecture that has no meaning. So they're just vectors without any connection. The only thing that you can use is the distance from one vector to other. And I think it's better to explain like in examples. So in this vector symbolic architecture setting, you have several operations like binding and bundling, for example. Binding, given two vectors, give you another one, which is pseudo-orthogonal to the first two vectors. And bundling, like given a bundle of vectors, this resulting vector will be closer to each of this vector in this bundle than to others vectors. And then we can use like these operations like binding and bundle to construct special representation of a scene. And this like due to the encoding. So if we encode, like you asked about position, like left or right. So if we fix a special vector for the like x0 position, and then other positions we will encode with permutation with vector or like cyclic shifting. So then in this relationships with this like first vector, this will be encoded. So I mean, it's not like given from data; it's given by construction. So and we can use this this power to reason on it. So when we say about like attribute red or color attribute and value red, we just randomly sample the hyperdimensional space to get these vectors. Like we don't use any neural networks or other stuff. So you have to think about this like of two different kinds of embeddings. That's it.
Okay. So Dr. Kovalev, I was curious about how the group level significant network in your architecture relates to the individual meaning network. I know you didn't talk about that a lot in your paper, but I think it's relevant to, you know, cognitive architectures in general. So how do these influence each other?
In significance network, we store information that's available to all agents in a group. So this is based on the theory of Vygotsky, that we have a culture approach. So there is information that's available to everyone in a group. And in meaning, we store the experience of our agents, and they connect it in terms of the agent can apply information like procedures from significant part to improve your meaning part. So like in this case. That's it.
Okay. All right. So Dr. Kolonen, how does your system compare with Q-learning on the potential for transfer learning? Does your system have the potential for generality? That is, if, for example, there was a different board setup? And in what types of problems might Q-learning be more general or less general?
Well, I'm not much of an expert in Q-learning, actually, but you're talking about our system, as much as I understand the concept of transfer learning, our architecture is quite effective in it, I think, because it's based on rules and exactly most specific rules. So in case when we have a data set and some experience that our agent under our architecture has obtained while operating on one field with some task, and then we place it in some other experiment with where the environment is different and the goal is different and so on. The rule hierarchy will be used, but the rules that were used, the most specific rules that were used on the previous field would not be so specific, because the system will register that the environment has changed, the rules of the game have changed, and it would use the more general rules with which by definition have less success probability than the most specific rules, because that's how we define the probability inference in our model. So it would use more general rules that are applicable in this case, and while it would somehow attain goals on the second field, it would gain new experience and transfer those general rules that it uses in the moment to new, most specific rules, and they won't contradict with already existing rules for the previous board. They would exist concurrently and would be used in different cases, and so that's it. And talking about cases where Q-learning is better than our system, more general or something like that, I'm not so sure, but the case where Q-learning might be more effective is the task that when you have the tasks when you need if we're talking about experiments similar to ours, when you have a square field with a lot of squares, maybe it's tasks when you need to take into account the whole field at all and not small area, and maybe in this case, the Q-learning, which is, as far as I know, which uses weights for every single square, might be more effective and might learn more quickly, maybe. But in other cases, I think our approach is more useful, more effective, and that's my vision of it. Thank you.
Okay, Dr. Du, you have used competition to change a planned process based on type. So what role do metrics for the quality of the plan have in the competition? And how does attention lead to better plans, for example?
Thank you for the question. Currently, what we so how competition affects plan currently right now is actually so it's actually through filtering. So imagine, so in the plan you will have a set of predicates where you will need to choose an action. You will set of predicates and you will choose your action based on what is the interest set or state. So what will happen is attention will actually try to constrict this problem space, and the planner will just work on this restricted space that we have. So in a sense, in terms of quality of the plan, we are still working on it. We do not really have a strict metric. To us, as long as the goal type, we have a goal type for that is achieved by the system, the system wants. As long as this goal type is achieved, we will consider this as a plan and we will execute it as it is. Going forward, however, is that one is quality of the plan that we want to choose, and next, another thing about it is how we want competition to be act more as a filter, more than a filter than currently what it is right now.
Okay, and finally, Dr. Ozkural, in your paper, you listed many parts of your architecture. But right now, I don't really see by what overall principle do these work together. What aspects of self-organization does your system incorporate? And how does your system learn subproblems, for example? And does knowledge of these solutions accumulate?
Oh, so that's all explained in the paper, but I suppose to fully understand it, you would have to read the alpha paper as well, but it's in the presentation, but let me repeat. The organizational principle is using universal induction over several reference machines. So this results in using not just one kind of program representation, like say neural networks, but also stochastic logic or functional programming representation to try to solve a machine learning problem. Okay, and the problem solving methods can use any of these reference machines to try to solve a particular task. And now to achieve the generality principles explained in the presentation, which are roughly completeness, modularity, model diversity, data type independence, task independence, domain independence, self-improvement, and agency. The kernel gives you completeness, so it's universal. It's a universal induction approximation. It has model diversity because you have a lot of models in problem-solving methods, and you have many reference machines which represents a very, very wide spectrum of representations. It has modularity because it has problem-solving methods as separate entities. They are it's a modular system, and this is actually most simply understood as a neurosymbolic architecture. So For instance, it can represent a scene as logical statements and functional relations and deep learning style pattern collections at the same time. This was also an idea in OpenCog, right? So the synthesis module can merge the low-level pattern representations in MetaNet deep learning component with more high-level relations learned, say like geometric relations represented in probabilistic logic. Of course, you'd have to train this, right? So you need many examples to train this. And one of the approaches here is to use unsupervised learning as much as possible. So that's an additional organizational principle. But the analysis and synthesis modules work like this. When you train the system, solve a new problem, it looks at its task performance memory. And task performance memory is a record of how well each problem-solving method performed on a problem. So it uses, again, machine learning to correlate the new problem with the past problems this way. And after each task is solved, it records performance and updates the memory. So it has to have a kind of transfer learning to do this, of course. And this is already done, by the way, in deep learning. So it's not very fantastical or infeasible. Stuff like this is just more general, to be honest. So say if you can recognize text, if you have a text model, okay, and if you have a problem specification in text, if you can recognize like similarities in text, you can do this. If you can't, then you can't do it. If you have a problem stated in a formal language, and if you have a deep learning model that can represent this formal language, then this, and these already exist, then this approach will work because it will be able to analyze this, break down into components, right? Because the deep learning representations are compositional. So it will be able to do that. And then if it can break down a problem into subproblems, and if it knows how to approximately solve a subproblem, looking at its task performance memory, and it says, oh, I solved this problem in the past, a similar problem, with a probabilistic logical language representation. So it recalls that. And I solved this by applying time series prediction using this probabilistic logical language representation. And it used these data types, and it was in this domain. And it was this sort of task. So it remembers all that, because we taught these to the system, and then tries to use a similar configuration to solve that subproblem, and other subproblems treated likewise. And then it tries to merge these subproblems, again, using its extremely modular architecture. So this is basically how it's supposed to work. I know this sounds like a lot of hand waving, like the get-out machine architecture, but this is the best I can do at this introductory level. I'm sorry, like the models actually used are pretty complex. I'm trying to simplify as much as possible. So the feasibility or success of this approach depends exclusively on the possibility or the reality of the AI kernel I'm alluding to. If it doesn't work, none of this stuff ever takes off. So the most interesting idea actually. The basis of the architecture is the relation of the AI kernel to other components. So there's a lot of, you can think of the AI kernel just as TensorFlow, okay? Something like TensorFlow. But it's supposed to be a little more complex. So in this iteration, I refer to Fourier network search, which can be used for meta learning, for learning a network architecture. You can extend Fourier network search to work with those other languages too. So it can pretty much represent any of those things, right? Theoretically. And then you can also use genetic algorithms or evolutionary computation to do things that deep learning won't give you easily. Good variation over models. And then at the very lowest level, for learning parameters of a complex model, you can use stochastic gradient descent. So this algorithm combination with powerful models, powerful generative models. So what I used in the past was, say, stochastic context-free grammar or context-sensitive grammar. So those are generative models, right? So you have these powerful generative models that can represent the a priori program probabilities of various reference machines. And this was actually tried and seemed to be very effective, super effective approach by the DARPA explainable AI project. So they made a few experiments that definitely verify what I introduced in 2018. So that was the first version on arXiv, if you look at it. So they were able to combine, and it's very similar to my own experiments, experimental setups. They were able to combine deep learning with scheme-like language. Whether scheme or my favorite language, OCaml, or some other language is the best for representing high-level computations is moot. They're all universal. It doesn't matter, okay? But still, inventing ever more efficient, effective program representations is important. So that's another really critical point. So if you can do this and you can support all those reference machines, this approach will definitely work, and it will get very close to or achieve human level AI. As current experiments do suggest that.
Hi. Okay. So I've been told that we have to finish really soon. So we just have one general question for everybody. So given the many different interesting approaches and cognitive architectures taken by each of you, what new ideas have you learned about that you might be interested in incorporating in your own work after hearing about and reading each other's ideas? Would anyone like to volunteer an answer?
Very shortly, I think hyperdimensional representations clarify, the mathematical basis of the deep learning sort of approaches. So this helps me understand it better, and maybe we can extend it further, this general approach. And also, I like to say machine reasoning sort of approaches, or the Hebbian neural net kind of machine reasoning approaches. That looks like a really powerful tool, and it should probably be included in a cognitive architecture.
I'll go next then. Dr. Kolonin's functional systems theory is actually very interesting. I see some similarity to what we have for process decomposition, and this is the first time I heard about functional systems theory, so I would like to explore that further.
Great.
Well, I would answer next. I have seen many different interesting solutions. Some of them I have seen before when studying the area. Some of them are fresh for me, are new. But for the moment, I know maybe my vision is restricted, but there's some background noise for the moment. Oh, so but I have not seen the things that that solve any of problems that we have for now. There are two of them, in my opinion, that we should work on. Is the first is how to achieve goals for the first, and how to gain the initial experience when you don't have it. So it's what that is called the orienting investigative reaction in Terra functional systems, and we're working on that. And the second thing is what if the needs to achieve the goal are changing periodically, like day and night, and there are several modes in the same environment when you have when you have two or more cases in which the goal achievement patterns are totally different, and how to gain some logic in that case. And I might maybe if I would study other works, other architectures more deeply, I would find some ideas for that. But for now, they are unsolved. But still, every single architecture is pretty interesting. Thank you.
Well, it takes time to absorb new ideas and try to apply it to like your own architecture. So I think I'm not ready to answer it right now, but our works are very, very interesting. And thank you.
Well, thank you so much. This concludes panel 1, Cognitive Architectures. We had some great papers to talk about.